Imagine standing outside tonight. Above you is an enormous universe filled with stars, galaxies, nebulae, black holes, and worlds we may never visit. And yet, beneath your feet is a planet that is every bit as extraordinary. Earth. We see it every day. We walk across it. We drink its water. We breathe its atmosphere. We watch its clouds move across the sky. Because Earth is so familiar, it can be easy to forget just how strange it really is. This planet is moving through space at incredible speeds. Its surface is constantly changing. Its continents move. Its oceans circulate enormous amounts of heat around the world. Its atmosphere is a thin layer of gas separating life from the vacuum of space. Deep below us is a gigantic interior of rock and metal, reaching thousands of kilometers toward the center. And somehow, on this particular world, chemistry became biology. Life appeared. It evolved. It diversified. And eventually, one species became capable of looking back at its own planet and asking, how did all of this happen? In this video, we're going on a long journey through Earth. We'll travel backward in time to the violent birth of our planet. We'll descend into its mysterious interior. We'll explore the deepest oceans, the highest mountains, the driest deserts, and the strangest places where life survives. We'll discover that Earth's atmosphere is far thinner than it looks. We'll learn why the sky is blue, why sunsets can turn red, why Earth has seasons, and why our planet isn't actually a perfect sphere. We'll look at earthquakes, volcanoes, hurricanes, glaciers, rivers, forests, deserts, and the gigantic geological forces that have shaped the world beneath our feet. And we'll travel billions of years into the past and eventually billions of years into the future. Because Earth isn't just a place. It is a dynamic planetary system, and the more we learn about it, the stranger it becomes. So get comfortable, dim the lights, and let's begin our journey through some of the most fascinating facts about the Earth. Chapter 1: Earth is not actually a perfect sphere. When you look at photographs of Earth from space, the planet appears almost perfectly round. But technically, Earth is not a perfect sphere. It is slightly flattened at the poles and bulges around the equator. This shape is called an oblate spheroid. The reason is simple. Earth rotates. As the planet spins, centrifugal effects cause material around the equator to move slightly outward. The difference isn't enormous, but it is measurable. Earth's equatorial diameter is roughly 43 kilometers greater than its polar diameter. That means if you could somehow measure Earth from pole to pole and then across the equator, you would find that the equatorial measurement is larger. But even this description isn't completely accurate. Earth's actual shape is more complicated. Mountains, ocean trenches, continents, ice sheets, and variations in the density of rocks all slightly alter the planet's gravitational field. Scientists, therefore, use a more complex concept called the geoid to describe Earth's physical shape. In other words, Earth isn't a perfectly smooth blue marble. It's a dynamic, irregular world covered by mountains, valleys, oceans, ice, and constantly moving geological structures. And there's another surprising fact. Earth isn't even rotating at exactly the same speed all the time. Its rotation changes slightly because of interactions between the atmosphere, oceans, Earth's interior, and the moon. Over very long periods, however, the moon's gravitational influence causes Earth's rotation to slow. Billions of years ago, Earth's days were considerably shorter. So when you say that a day lasts 24 hours, you're describing an average familiar to modern humans, not a permanent property of the planet. Earth itself has changed dramatically throughout its history. And this is one of the most important ideas to remember during our journey. Nothing about our planet is completely static. Earth is alive with motion. Chapter 2: Earth is moving extremely fast. Right now, you may feel completely stationary. You're sitting in a chair. Maybe you're lying in bed. Perhaps you're watching this video on your phone or computer. But you're actually moving at several different speeds simultaneously. First, Earth rotates around its axis. At the equator, the surface moves at roughly 1,670 kilometers per hour because of Earth's rotation. But that's only the beginning. Earth also travels around the Sun. Its average orbital speed is approximately 107,000 kilometers per hour. That means Earth is racing around the Sun while simultaneously spinning. But even that isn't the complete picture. The Sun itself is moving through the Milky Way galaxy. And the Milky Way is moving through the larger cosmic environment. So there is no simple sense in which you are standing still. You are participating in several enormous cosmic motions at once, and yet you don't feel them, huh? Why? Because you, the atmosphere, the oceans, buildings, trees, and everything around you are moving together. You mainly notice motion when there are changes in speed or direction. A smooth airplane cruising at constant speed can feel almost stationary. Earth's motion is similarly smooth. So while you watch this video, you're effectively traveling through space on a giant rotating and orbiting world. And there's something even more amazing. You don't have to leave Earth to experience the consequences of its motion. The rotation of the planet helps create the day-night cycle. Earth's orbit around the Sun helps create the length of our year. The tilt of Earth's rotational axis gives us seasons. And the planet's movement through space helps determine the environment in which life exists. The ground beneath your feet may feel motionless. Cosmically speaking, it absolutely isn't. Chapter 3 Earth is about 4.5 billion years old. Earth is ancient, incredibly ancient. The planet formed approximately 4.5 billion years ago. To understand how long that is, imagine compressing the entire history of Earth into a single calendar year. Earth forms on January 1st. For most of the year, the planet is dominated by geology and microscopic life. Complex animals appear extremely late. Dinosaurs don't appear until near the end of the year. And humans arrive in the final moments of December 31st. Modern human civilization would occupy only a tiny fraction of the final seconds. This comparison reveals something profound. Human history feels long to us because our lives are short. But on geological timescales, human civilization is extremely recent. Earth itself has experienced enormous transformations. There were periods when the planet was almost completely frozen. There were periods when atmospheric conditions were radically different. Continents have collided, separated, and moved thousands of kilometers. Entire mountain ranges have risen and eroded away. Oceans have opened and disappeared. Species have appeared and vanished. And through all of this, Earth continued its journey around the Sun. Scientists determine Earth's age using several independent lines of evidence, including radiometric dating of ancient rocks and meteorites. Some of the oldest minerals discovered on Earth are more than 4 billion years old. Meteorites provide another important clue because many formed during the early history of the solar system. Their ages are consistent with the solar system, roughly 4.6 billion years old. Earth formed shortly afterward. So every rock, mountain, ocean, and living organism on our planet exists within an extraordinarily long story. The world we see today is only one temporary chapter. Chapter 4. Earth was born from cosmic debris. Earth did not begin as a beautiful blue planet. The early solar system was a chaotic environment filled with gas, dust, rocks, and growing planetary bodies. Around the young sun, microscopic particles collided and stuck together. Over enormous periods of time, these particles formed larger objects. Those objects collided again. Eventually, some became planetesimals and then protoplanets. One of those growing worlds became Earth. The early Earth was hot, very hot. Frequent collisions released enormous amounts of energy. Radioactive elements inside the young planet also contributed heat. As Earth became sufficiently large, gravity pulled material inward and helped separate it according to density. Heavy materials, especially iron, moved toward the center. Lighter silicate materials remained closer to the surface. This process eventually produced Earth's layered structure core, mantle, crust. But the early Earth was still radically different from today's planet. There were no forests, no birds. No oceans filled with fish, no cities, no familiar blue sky. The surface was subjected to intense volcanic activity and impacts from other objects in the young solar system. One of the most important events in Earth's early history may have been a gigantic collision involving a Mars-sized body. The debris from this collision eventually came together to form the Moon. That event may have dramatically changed Earth. The Moon became Earth's largest natural satellite. Its gravity influences ocean tides. It helps stabilize Earth's axial orientation over long timescales. And it became a major feature of the night sky. So when you look at the Moon, you're looking at a companion whose history is deeply connected with the formation of our planet. Chapter 5. The Moon is part of Earth's story. The Moon is unusually large compared with its planet. Many planets have moons, but Earth's moon has a substantial mass relative to Earth. Its gravitational influence reaches across the planet. One of the most obvious consequences is the ocean tide. The Moon's gravity pulls on Earth's oceans. The Sun contributes as well. When the gravitational effects of the Sun and Moon align, we experience stronger tidal ranges called spring tides. When they partially counteract each other, we get weaker neap tides. But the Moon does more than move ocean water. It also influences Earth's rotation. Tidal interactions transfer rotational energy from Earth into the Moon's orbital motion. As a result, Earth's rotation has gradually slowed over geological time. Meanwhile, the Moon is slowly moving farther away from Earth. The change is tiny on a human timescale, but over millions and billions of years, it becomes significant. The Moon also produces spectacular eclipses. A solar eclipse occurs when the Moon passes between Earth and the Sun. A lunar eclipse occurs when Earth passes between the Sun and Moon. The apparent sizes of the Sun and Moon in Earth's sky happen to be remarkably similar. That is why total solar eclipses can occur, with the Moon temporarily covering the Sun's visible disk. This is a beautiful example of cosmic geometry. The Moon is also slowly becoming less important in some respects as it moves farther away, but its influence remains enormous. And without the Moon, Earth would be a somewhat different planet. The history of our world cannot be completely separated from the history of its satellite. Chapter 6. Earth's atmosphere is a thin shell. From the ground, the atmosphere seems enormous. The sky stretches from horizon to horizon. Clouds can tower kilometers above us. Storm systems can become thousands of kilometers wide. Yet compared with the size of Earth, the atmosphere is remarkably thin. If Earth were represented by a large apple, the atmosphere we depend on would be more like a very thin skin surrounding it. The atmosphere is held in place by gravity. It contains mostly nitrogen and oxygen, along with smaller amounts of other gases. Water vapor varies greatly depending on location and weather. Carbon dioxide and other trace gases exist in much smaller concentrations, but can have important effects on Earth's climate. The atmosphere performs many functions simultaneously. It provides oxygen for aerobic life. It helps regulate temperature. It transports water. It creates weather. It blocks or absorbs certain types of radiation, and it burns up many small meteoroids before they reach the surface. The atmosphere also doesn't simply stop at one sharp boundary. It gradually becomes thinner with altitude. Different layers are defined according to temperature behavior and other properties. The troposphere is the layer where most weather occurs. Above it is the stratosphere, which contains the ozone layer. Higher still are the mesosphere, thermosphere, and extremely diffuse outer regions. What we call space is therefore not separated from Earth by a perfectly sharp wall. The transition is gradual, and that makes Earth's atmosphere even more remarkable. Every breath you take comes from a thin planetary envelope, a relatively fragile layer that supports nearly every ecosystem we know. Chapter 7W. Why is the sky blue? One of the most familiar sights on Earth is also a demonstration of physics. The blue sky exists because sunlight interacts with Earth's atmosphere. Sunlight may appear white, but it contains many wavelengths of visible light. When sunlight enters the atmosphere, molecules in the air scatter the light. Shorter wavelengths, particularly blue light, are scattered more strongly than longer wavelengths such as red. This process is known as Rayleigh scattering. Because blue light is scattered in many directions, the sky appears blue when viewed away from the sun. But the sky doesn't always look blue. At sunrise and sunset, sunlight travels to a longer path through the atmosphere. Much of the shorter wavelength light is scattered away from the direct path. The remaining direct sunlight can therefore appear increasingly orange or red. Particles and aerosols in the atmosphere can dramatically affect the appearance of sunsets. Volcanic eruptions, wildfire smoke, dust, and pollution can all influence atmospheric scattering. This means every sunrise and sunset is partly a product of the atmosphere's current physical condition. The colors we see are not painted onto the sky. They are produced by light interacting with matter. And this leads to another beautiful fact. The sky isn't inherently blue. An observer on another planet could see an entirely different color depending on atmospheric composition, pressure, particles, and the light from its star. Earth's blue sky is a consequence of the particular combination of our atmosphere and our sun. Chapter 8. Earth has an enormous ocean. Around 71% of Earth's surface is covered by water. That is why Earth is often called the blue planet. But the oceans are more than a beautiful surface feature. They are one of the planet's major climate engines. Ocean water absorbs enormous amounts of solar energy. Ocean currents transport heat around the world. Evaporation transfers water from the ocean into the atmosphere. That water eventually falls as precipitation. Some returns directly to the ocean, that some flows across land through rivers. Some becomes trapped in glaciers and ice sheets. Some infiltrates underground. The global water cycle connects the atmosphere, oceans, land, ice, and living organisms. And most of Earth's water is not fresh water. The overwhelming majority is salty ocean water. Only a small fraction is readily available as fresh water. Much of Earth's fresh water is locked in glaciers and ice sheets or stored underground. Another fascinating fact is that the deepest parts of the ocean are extraordinarily deep. The deepest known ocean trenches extend nearly 11 kilometers below sea level. If Mount Everest were placed inside the deepest ocean trench, its summit would still be underwater. And despite decades of exploration, enormous portions of the deep ocean remain poorly understood. Scientists continue discovering new species and unusual ecosystems. In the darkness thousands of meters below the surface, life survives without sunlight. This is possible partly because of chemical energy sources associated with hydrothermal vents. The deep ocean reminds us that Earth can remain mysterious even on our own planet. We don't need to travel to another star to find alien-looking environments. Sometimes we only need to descend into the darkness beneath the waves. Chapter 9. The deepest place on Earth. The deepest known parts of Earth's oceans are found in deep ocean trenches. Among them, the Mariana Trench is famous for reaching extreme depths. The deepest known point, Challenger Deep, is nearly 11 kilometers below sea level. At that depth, the pressure is immense. It is hundreds of times greater than the atmospheric pressure at Earth's surface. A human being without a specialized pressure-resistant vehicle would not survive. Yet life exists there. Microorganisms, small animals, and other specialized organisms have adapted to extreme pressure. Darkness, cold, and limited food. This demonstrates something important about life. Life on Earth is extraordinarily adaptable. We often imagine habitability as something requiring comfortable temperatures, abundant sunlight, and familiar environments. But Earth's biosphere repeatedly challenges those assumptions. Organisms live in boiling environments near hydrothermal vents. Others survive in Antarctic ice. Some live kilometers beneath Earth's surface, some tolerate enormous pressure. Some can survive intense radiation or long periods without food. The deepest ocean, therefore, isn't merely a geographical extreme. It is a laboratory for understanding life's limits. And perhaps one day, these organisms could help us understand where life might exist beyond Earth. If life can survive in darkness, under enormous pressure, and without sunlight, then perhaps environments that appear hostile at first glance may deserve a second look. Earth keeps expanding our definition of what habitable can mean. Chapter 10. Earth's mountains are constantly changing. Mountains look permanent. A mountain range can appear timeless. But geologically speaking, mountains are temporary structures. They are continuously being built and destroyed. Some mountains form when tectonic plates collide. When continental crust is compressed, rocks can fold, fracture, and rise. The Himalayas are a spectacular example. The Indian plate continues interacting with the Eurasian plate, and the region remains tectonically active. But while tectonic forces build mountains, erosion works against them. Wind removes material. Rain cuts channels. Rivers transport sediment. Glaciers carve valleys. Freeze-thaw cycles break rocks apart. Over millions of years, mountains can be dramatically reshaped. The highest mountain above sea level is Mount Everest. But if we measure from the base of a mountain rather than sea level, the answer can change. Mauna Kea in Hawaii rises dramatically from the ocean floor, making its total vertical height from base to summit greater than Everest's height above sea level. This illustrates a larger point. There isn't always one simple definition for highest or deepest. It depends on what measurement you choose. Earth's surface is a complex three-dimensional landscape. And beneath that landscape, the planet continues moving. The continents themselves are not fixed. They travel across Earth's surface at speeds comparable to the growth rate of human fingernails. Slow? Yes. But over millions of years, those tiny movements completely transform geography. Chapter 11. Continents are moving right now. The continents beneath our feet feel permanent. They are not. Earth's outer shell is divided into large tectonic plates. These plates move over the hotter, weaker material beneath them. The movement is usually only a few centimeters per year. That sounds insignificant. But imagine repeating that movement for 100 million years. Several centimeters per year can become thousands of kilometers. This process has repeatedly rearranged Earth's continents. In the past, many of today's continents were joined together. One famous supercontinent was Pangaea. Eventually, Pangaea broke apart. The pieces continued moving. The Atlantic Ocean expanded. Africa moved relative to South America. India traveled northward before colliding with Asia. Australia moved away from Antarctica. The map of Earth has therefore never been permanent. If humans could somehow travel 200 million years into the future, the world map would look dramatically different. New oceans could open. Existing oceans could shrink. Mountain ranges could rise. Others could disappear. Continents could collide again. Earth's surface is essentially a gigantic geological puzzle that is constantly rearranging itself. And this movement is responsible for much more than geography. Plate tectonics helps create mountains. It produces earthquakes. It contributes to volcanoes. It recycles crust. It influences the long-term carbon cycle. And it plays a major role in Earth's geological evolution. The continents may look still, but underneath them, Earth is moving. Chapter 12. Earthquakes are releases of stored energy. An earthquake can last only seconds, but those seconds can release enormous amounts of energy. Most earthquakes occur when stress accumulated in Earth's crust is suddenly released. Tectonic plates are constantly moving, but their boundaries don't always slide smoothly. Friction can cause rocks to lock together. Stress builds. Eventually, the rocks can rupture or slip. Energy travels outward as seismic waves. The ground shakes. Most earthquakes are small and go unnoticed. Others are powerful enough to reshape landscapes, damage buildings, trigger landslides, and generate tsunamis. Scientists use seismometers to detect and analyze these vibrations. Seismic waves can also reveal what lies inside Earth. Some waves travel through solids. Others cannot pass through liquids. By observing how seismic waves travel through Earth, scientists have inferred the structure of the planet's interior. In a strange way, earthquakes allow us to see deep inside Earth without drilling there. And Earth has a remarkable record of seismic activity. There are earthquakes happening somewhere on the planet every day. The vast majority are harmless. But the largest events remind us that Earth is not geologically quiet. The ground beneath us is part of a dynamic planetary system. When an earthquake occurs, it isn't Earth randomly shaking. It is the visible consequence of enormous geological forces acting over years, centuries, and millions of years. Chapter 13. Volcanoes build and destroy. Few geological phenomena are as dramatic as a volcano. A volcano can transform landscapes. It can create new land. It can destroy cities. It can release gases and ash high into the atmosphere. And it provides a direct connection between Earth's surface and its hot interior. Magma is molten rock beneath the surface. When magma reaches the surface, it becomes lava. Volcanic eruptions vary enormously. Some produce relatively gentle flows. Others generate explosive eruptions that send ash and gases high into the atmosphere. Volcanic islands are often created through repeated eruptions. Over time, layers of lava accumulate. Eventually, a volcanic mountain can rise from the ocean. Hawaii is one example of a volcanic island chain created by enormous geological processes. Volcanoes also occur along tectonic plate boundaries. At subduction zones, one plate can sink beneath another. Water and other materials carried downward can influence melting in the mantle and contribute to magma formation. Volcanism has shaped Earth throughout its history. It has contributed to the creation of continents and oceanic crust. It has released gases that became part of the atmosphere. It has influenced climate. And it continues today. When you see a volcanic mountain, you're looking at a geological system that may extend deep into Earth's interior. A volcano isn't simply a mountain with a hole. It is a pathway through which our planet releases heat and material. Chapter 14. Earth has a magnetic shield. Earth has something that many planets would love to have: a global magnetic field. It is generated primarily by movements of electrically conducting molten metal in Earth's outer core. This process is known as the geodynamo. The magnetic field extends far beyond the atmosphere and creates a region called the magnetosphere. The magnetosphere interacts with the solar wind, the continuous flow of charged particles coming from the sun. This interaction helps protect Earth from some of the effects of the solar wind. The magnetic field isn't a rigid shield. It can be compressed, distorted, and disturbed by solar activity. During powerful solar storms, changes in the magnetosphere can produce spectacular auroras. Auroras occur when energetic charged particles interact with gases in the upper atmosphere. Near the poles, these interactions can produce curtains of green, red, purple, and other colors. Earth's magnetic field has also changed throughout geological history. The magnetic poles move. And Earth's magnetic field has reversed polarity many times in the distant past. During a reversal, magnetic north and magnetic south effectively switch. These reversals don't happen according to a simple predictable schedule. They are recorded in rocks that preserve the direction of Earth's magnetic field when they formed. So even the invisible magnetic environment surrounding Earth leaves evidence behind in the rocks beneath our feet. Chapter 15. Earth's interior is extreme. We live on Earth's surface. But the surface is only a tiny fraction of the planet. Earth's interior is divided into several major layers. The crust is the thin outer shell. Below it lies the mantle. Deeper still is the core. The mantle is mostly solid rock, but over geological timescales, it can deform and flow. The outer core is liquid metal. The inner core is solid. Temperatures deep inside Earth are extremely high. Pressure is also enormous. The inner core remains solid despite its high temperature because the pressure is so intense. Earth's core is composed primarily of iron, along with other elements. The outer core's motion generates the planet's magnetic field. We cannot simply drill to the core. Human drilling has reached only a tiny fraction of the distance to Earth's center. Instead, scientists use indirect evidence. Seismic waves provide some of the most important information. Earthquakes send waves through the planet. The behavior of these waves reveals changes in density and physical state. Gravity measurements provide additional information. Laboratory experiments allow scientists to study materials under extreme pressures and temperatures. Computer models combine these observations. Together, these techniques give us a remarkably detailed picture of a world that humans have never physically visited. The center of Earth is nearly 6,400 kilometers beneath us. And yet, its influence reaches the surface. The heat inside Earth powers geological activity. The movement of its outer core generates the magnetic field. The mantle participates in tectonic processes. So even though Earth's interior is hidden, it controls many features of the world we see. Chapter 16. Earth has water deep inside it. When we think about Earth's water, we usually imagine oceans, lakes, rivers, glaciers, and clouds. But some water is also stored deep within Earth's interior. Certain minerals in the mantle can incorporate hydrogen and oxygen into their crystal structures. This doesn't mean there is a giant underground ocean sloshing around beneath us. Instead, water can be chemically bound within minerals. This hidden reservoir is important because it demonstrates how complex Earth's water cycle really is. Water doesn't simply move between clouds, rivers, and oceans. It can interact with rocks. It can enter the crust. It can be transported downward at tectonic plate boundaries. It can eventually return toward the surface through geological processes. This creates connections between Earth's surface and interior. Scientists are still working to understand exactly how much water exists deep inside Earth and how it moves through the planet. The discovery of water-bearing minerals at great depths has changed how scientists think about the global water cycle. The surface of Earth may therefore represent only part of the planet's total water system. Our planet is more interconnected than it first appears. The ocean touches the atmosphere. The atmosphere interacts with glaciers. Glaciers feed rivers. Rivers carry material to oceans. Oceans interact with the crust. Tectonic processes transport material into Earth's interior. And geological processes eventually bring some of it back. Earth is not a collection of separate systems. It is one enormous interconnected machine. Chapter 1:7 Earth's climate has changed dramatically. Earth has never had one permanent climate. Throughout geological history, the planet has experienced ice ages, greenhouse periods, warm intervals, and dramatic climate transitions. There were times when glaciers covered enormous portions of the planet. There were also periods when Earth's average climate was significantly warmer than today. The climate system is influenced by many factors. Solar energy. Atmospheric composition, volcanic activity, ocean circulation. Ice cover, continental arrangement, clouds, vegetation, and long-term changes in Earth's orbit and axial orientation. One famous example is the sequence of ice ages during the Pleistocene. Large ice sheets repeatedly expanded across parts of North America and Eurasia. Sea levels fell as enormous quantities of water became locked in ice. Then the climate warmed. Ice retreated. Sea levels rose. Landscapes changed. Species migrated, and ecosystems transformed. These changes occurred over thousands to millions of years. Earth's climate is therefore not a static background condition. It is a complex physical system. Small changes in one component can influence others. For example, ice reflects sunlight. Less ice can mean more sunlight is absorbed by the surface. That can contribute to further warming. This is an example of a climate feedback. Understanding Earth's climate requires understanding the interactions between atmosphere, ocean, ice, land, and life. And that complexity is one reason earth science remains an active field of research. Chapter 18. The planet has experienced snowball Earth. One of the strangest periods in Earth's history may have occurred hundreds of millions of years ago. Evidence suggests that Earth experienced episodes of exceptionally extensive glaciation. These periods are sometimes described using the dramatic term snowball Earth. The basic idea is that ice may have covered much of the planet, potentially extending into low latitudes. If Earth's surface becomes heavily covered in ice, more sunlight is reflected back into space. That can encourage further cooling. More cooling can produce more ice. This creates a powerful positive feedback. But Earth eventually escaped these frozen states. Volcanic activity continued even when much of the surface was covered by ice. Volcanoes release carbon dioxide. Over very long periods, atmospheric carbon dioxide can accumulate if weathering and biological processes cannot remove it rapidly enough. Eventually, greenhouse warming may have become strong enough to melt the ice. The precise details remain an active area of scientific investigation. But the possibility of a nearly frozen Earth demonstrates how dramatically planetary climate can change. The blue planet we know today may have once looked very different. A world of ice, a world of volcanoes, a world where the conditions for life were radically altered, and yet life survived. That survival tells us something remarkable. Life on Earth has endured enormous environmental changes. Chapter 18. The planet has experienced snowball Earth. When people hear the word desert, they often imagine hot sand. But deserts are defined primarily by dryness, not temperature. Some deserts are extremely cold. Antarctica is technically the largest desert on Earth because it receives very little precipitation. The Antarctic interior is brutally cold and extremely dry. At the other extreme are hot deserts such as the Sahara. The Sahara is one of the largest hot deserts on Earth. Its landscapes include sand dunes, rocky plateaus, mountains, gravel plains, and dry valleys. Deserts can appear lifeless, but they are not. Specialized organisms have evolved to survive with extremely limited water. Some plants have deep roots. Others store water. Some animals are nocturnal, avoiding the intense daytime heat. Microorganisms can survive in environments that seem almost completely barren. Deserts also change over time. The Sahara has not always looked the way it does today. Climate changes have repeatedly transformed parts of North Africa. At certain times in the past, regions that are now deserts supported grasslands, lakes, wetlands, and abundant wildlife. Ancient rock art provides evidence of people living alongside animals that are no longer common in the region. This is another reminder that today's Earth is only one moment in a much longer climate story. A desert is not simply empty land. It is an ecosystem shaped by water scarcity. And life has learned to survive there in extraordinary ways. Chapter 2. Antarctica is a continent of extremes. Antarctica is the coldest continent on Earth. It is also the driest and one of the windiest. Most of the continent is covered by a gigantic ice sheet. This ice contains a large fraction of Earth's fresh water. The Antarctic ice sheet is so massive that its weight presses the underlying crust downward. If the ice disappeared, the land beneath would gradually rise in a process called isostatic rebound. Antarctica also contains mountain ranges, active geological regions, and enormous subglacial lakes hidden beneath kilometers of ice. Perhaps most fascinating is what happens at the boundary between ice and ocean. Large ice shelves extend from the continent into surrounding seas. These shelves can act as buttresses that slow the movement of inland ice toward the ocean. Antarctica is not frozen solid in every sense. Beneath the ice, liquid water can exist. Geothermal heat and pressure can contribute to melting at the base. Scientists use radar and other techniques to map what lies beneath the ice. In some locations, ancient landscapes are preserved beneath layers of ice that have accumulated over immense periods. Antarctica, therefore, contains a hidden world beneath its frozen surface. And because the continent plays an important role in Earth's climate and sea level system, understanding Antarctica is critical to understanding the future of the planet. Chapter 2.1. The Amazon is more than a forest. The Amazon rainforest is one of Earth's most important ecosystems. It covers a vast region of South America and contains extraordinary biological diversity. Millions of species may inhabit tropical forests, including many that have not yet been scientifically described. The Amazon also plays a major role in the global water cycle. Trees absorb water from the soil and release water vapor through a process called transpiration. This moisture contributes to clouds and precipitation. In other words, the forest doesn't merely receive rain. It also helps influence the movement of water through the atmosphere. The Amazon River system is enormous. The river carries vast quantities of fresh water toward the Atlantic Ocean. Its floodplain ecosystems change dramatically between wet and dry periods. The forest is also an enormous carbon reservoir. Trees and soils store carbon. But forests are dynamic. They grow, they die, they burn, they decompose. They interact with climate and human activity. The Amazon, therefore, isn't simply a collection of trees. It is a gigantic interconnected ecosystem involving atmosphere, water, soil, plants, animals, fungi, microorganisms, and climate. And some of its most important inhabitants are microscopic. Fungi and bacteria break down organic matter, and recycle nutrients. Without these organisms, forests could not function as they do. The Amazon reminds us that an ecosystem is not defined by its largest animals. It is defined by the network connecting everything together. Chapter 2:2. Life exists in extreme places. Earth's life is astonishingly adaptable. Microorganisms known as extremophiles can survive conditions that would kill most familiar organisms. Some live in extremely acidic environments. Others tolerate intense heat. Some survive extreme cold. Some thrive under enormous pressure. Deep beneath Earth's surface, microbial communities can exist far from sunlight. At hydrothermal vents on the ocean floor, ecosystems can be powered by chemical energy rather than sunlight. These environments transformed our understanding of what life requires. For a long time, sunlight seemed central to the idea of a habitable ecosystem. But hydrothermal vent communities demonstrated that biological systems can be supported by chemical energy. This matters beyond Earth. When scientists search for life on other worlds, they don't necessarily look only for Earth-like surfaces. They consider subsurface oceans, hydrothermal activity, chemical gradients, ice-covered environments, and other potential energy sources. Earth is therefore our natural laboratory for understanding extraterrestrial habitability. Every extreme environment we discover expands the range of conditions in which life might survive. The planet beneath our feet has repeatedly surprised us. And perhaps the greatest surprise is that life doesn't merely survive Earth. Life changes Earth. Chapter 23. Life has transformed the planet. Earth's atmosphere was not always oxygen-rich. Early Earth's atmosphere was dramatically different from today's. Then something extraordinary happened. Photosynthetic organisms began producing oxygen. Over geological time, oxygen accumulated in the atmosphere. This transformation is associated with the Great Oxidation Event roughly 2.4 billion years ago. Oxygen was toxic to many organisms that had evolved in oxygen-poor environments, but it also opened new possibilities. Aerobic metabolism can extract large amounts of energy from food. Eventually, oxygen-dependent ecosystems became widespread. The rise of oxygen also helped create the ozone layer in the upper atmosphere. The ozone layer absorbs much of the sun's harmful ultraviolet radiation. This created a more favorable environment for life on land. In this sense, life didn't simply adapt to Earth's atmosphere. Life helped transform it. This is one of the deepest lessons in Earth science. The planet and its biosphere are coupled. Rocks influence life, life influences rocks. The atmosphere influences organisms, organisms influence the atmosphere. Oceans influence climate, climate influences ecosystems. Everything interacts. Earth is not simply a rock with life sitting on top. It is a planetary system in which geology, chemistry, climate, and biology continuously interact. Chapter 2:4 Earth has had 5 mass extinctions. Life has survived several catastrophic periods. Scientists commonly recognize 5 major mass extinction events in the geological record. The largest occurred approximately 252 million years ago. It is known as the Permian-Triassic extinction. A huge proportion of marine and terrestrial species disappeared. The causes involved enormous environmental changes, including massive volcanic activity and climate disruption. Then came another famous event approximately 66 million years ago. The Cretaceous-Paleogene extinction ended the age of non-avian dinosaurs. An asteroid approximately 10 kilometers across struck near what is now the Yucatan Peninsula. The impact released enormous energy. Dust and aerosols entered the atmosphere. Global environmental conditions changed rapidly. Many species disappeared, but not all life was destroyed. Birds survived. Mammals survived. Crocodilians survived. Insects survived. Plants survived. And eventually, ecosystems recovered. The extinction of the non-avian dinosaurs created opportunities for mammals to diversify dramatically. Millions of years later, one branch of that mammalian evolutionary story would produce humans. This is one of the strangest facts about our existence. Our species is partly here because of a chain of events extending billions of years into the past. If certain evolutionary events had happened differently, the world might contain completely different organisms, perhaps no humans, perhaps something else. Earth's history is therefore not only a story of survival, it is a story of contingency. Chapter 25. Dinosaurs ruled Earth for a very long time. Humans often think of dinosaurs as ancient, and they were. But the amount of time separating us from dinosaurs is still difficult to comprehend. Non-avian dinosaurs first appeared more than 230 million years ago. They survived for more than 160 million years before the asteroid impact associated with the end Cretaceous extinction. Modern humans have existed for only a tiny fraction of that time. Even our entire civilization occupies almost nothing on this timeline. Dinosaurs lived through changing continents, changing climates, changing oceans, and evolutionary transformations that created enormous diversity. Some dinosaurs were tiny. Others were gigantic. Some walked on 2 legs, others on 4. Some were predators. Others were herbivores. And birds are living dinosaurs. This is an important scientific distinction. The extinction event, approximately 66 million years ago, did not eliminate dinosaurs completely. It eliminated non-avian dinosaurs. Birds survived. So every pigeon, eagle, chicken, penguin, and hummingbird you see today belongs to a lineage that traces back to dinosaurs. In a very real sense, dinosaurs never completely disappeared. They are still flying above us. Chapter 26. Earth has some enormous animals. Earth has produced some extraordinary giants. The blue whale is the largest known animal ever to have lived. It can reach lengths of around 30 meters or more and weigh well over 100 metric tons. That is larger than any known dinosaur in terms of body mass. The fact that such an enormous animal exists today is astonishing. And yet, the blue whale's environment is mostly hidden from us. It lives in oceans that cover most of Earth's surface. Other giants include elephants, giraffes, giant sequoias, and enormous fungal networks. The scale of life varies tremendously. Some organisms are microscopic. Others can stretch for kilometers. Some colonies and clonal organisms can persist for thousands of years. This makes the concept of an individual organism surprisingly complicated. A forest may contain millions of individual organisms interacting together. A coral reef is built by tiny animals working collectively. Fungi can form enormous underground networks. Life is therefore not simply a collection of individual creatures. It is a network of systems operating at many scales. From molecules to cells. To organisms. To ecosystems. To the entire biosphere. Earth is filled with life at every scale imaginable. Chapter 27. The oldest living organisms can be ancient. Some organisms live for extraordinarily long periods. Certain trees can survive for thousands of years. Some clonal colonies may be even older. This creates a fascinating contrast. Human generations come and go. Political systems rise and fall. Cities are built and abandoned. Yet an organism can remain alive through centuries of human history. Ancient trees record environmental changes in their growth rings. Scientists can use these records to reconstruct aspects of past climates. Tree rings can reveal droughts, temperature changes, fires, and other environmental conditions. Other natural archives perform similar functions. Ice cores preserve bubbles of ancient atmosphere. Sedimentary rocks record environmental conditions. Corals can preserve information about past ocean conditions. Lake sediments contain layers of biological and chemical evidence. Earth is therefore filled with natural archives. The planet keeps records of its own history. We simply need to learn how to read them. A tree can tell a story through its rings. An ice core can reveal ancient atmospheric gases. A rock can preserve evidence of an extinct environment. And fossils can show us organisms that disappeared millions of years ago. Earth is, in effect, a gigantic historical archive. Chapter 2.8 Earth's ice contains ancient air. Ice sheets can preserve bubbles of ancient atmosphere. When snow accumulates and becomes compressed into ice, tiny pockets of air can become trapped. Scientists can drill deep ice cores and analyze these bubbles. This allows researchers to study past atmospheric composition. In some locations, ice records extend hundreds of thousands of years into the past. The ice can contain information about greenhouse gases, dust, volcanic activity, and other environmental conditions. This is an extraordinary form of natural time travel. Imagine extracting a piece of ice and discovering a tiny bubble containing air from a world that existed before modern civilization. That air interacted with ancient forests. Ancient oceans, ancient animals. Ancient climates. And now, millions or hundreds of thousands of years later, humans can analyze it. Earth science often works this way. We cannot travel backward in time, but the planet has preserved evidence of its past. We can examine it, measure it, compare it, and reconstruct what happened. The deeper scientists go into some ice sheets, the older the trapped atmosphere becomes. The frozen surface, therefore, acts like a layered archive of Earth's environmental history. Chapter 29. Rivers are powerful sculptors. A river may look peaceful, but over thousands or millions of years, flowing water can transform entire landscapes. Rivers erode rock. They transport sediment. They carve valleys. They create canyons. They build floodplains and deltas. One of the most spectacular examples is the Grand Canyon. The Colorado River and other geological processes have carved deeply into the Colorado Plateau over immense spans of time. The result is a landscape revealing layers of Earth's geological history. Each exposed layer represents a different chapter. Some rocks formed in ancient seas. Others formed in deserts or river environments. Still others record volcanic or tectonic events. A canyon, therefore, isn't simply a hole in the ground. It can be a geological timeline. The deeper you look, the farther back in time you may travel. And rivers are constantly creating new geological records. Sediment carried downstream eventually settles. Over time, layers accumulate. They can later become rock. Millions of years later, erosion may expose those layers again. The cycle continues. Water is one of Earth's most powerful geological forces. It may seem gentle, but given enough time, water can carve mountains into valleys. Chapter 30. Earth has waterfalls, caves, and hidden worlds. Some of Earth's most spectacular environments are hidden underground. Caves form through geological processes involving water, chemical dissolution, lava, and erosion. Some cave systems extend for hundreds of kilometers. Others contain enormous chambers. Inside caves, organisms may live in complete darkness. Some have lost pigmentation. Some have reduced eyesight. Others have evolved highly specialized senses. Caves can also preserve geological structures that take thousands or millions of years to form. Stalactites and stalagmites grow slowly as mineral-rich water deposits material. Some underground environments contain rivers and lakes. Others connect to surface ecosystems through complex networks. One of the most spectacular cave systems known is Sen Hung in Vietnam, famous for its enormous chambers and unusual underground environment. These environments remind us that Earth's surface is not the entire planet. There is another world beneath us. A world of rock, water, darkness, minerals, and specialized life. Even today, new caves and underground ecosystems continue to be explored. Earth remains capable of surprising us despite centuries of scientific investigation. Chapter 3:1 Lightning is incredibly hot. A lightning bolt is one of nature's most spectacular events. A lightning channel can become extremely hotter than the surface of the sun for a brief moment. The intense heating causes surrounding air to expand explosively. That expansion produces the sound we hear as thunder. Lightning occurs when electrical charges separate within clouds or between clouds and the ground. The details are complex, but collisions among ice particles, water droplets, and other particles inside storm clouds contribute to charge separation. When the electrical potential becomes large enough, a discharge occurs. Lightning can travel enormous distances. Some lightning events occur entirely within clouds. Others connect clouds to the ground. And some rare forms of lightning extend upward into the atmosphere. Thunderstorms, therefore, operate across multiple layers of Earth's atmosphere. Lightning also plays a role in atmospheric chemistry. The extreme energy of a lightning discharge can drive chemical reactions involving nitrogen and oxygen. Those compounds can eventually enter ecosystems through precipitation and soil processes. So lightning isn't simply a spectacular flash. It is part of Earth's electrical and chemical systems. Chapter 32. Hurricanes are giant heat engines. Tropical cyclones are among Earth's most powerful weather systems. Different regions use different names. They may be called hurricanes, typhoons, or cyclones. These storms form over sufficiently warm tropical or subtropical ocean waters under favorable atmospheric conditions. Warm ocean water provides energy through evaporation. Water vaporizes and condenses. Condensation releases latent heat. That heat helps power the storm. Earth's rotation contributes to the storm's organization through the Coriolis effect. A mature tropical cyclone can develop enormous wind speeds and a distinctive spiral structure. The center may contain an eye where conditions are temporarily calmer. Around the eye is the eye wall, where some of the strongest winds and heaviest rainfall occur. These storms can be hundreds of kilometers across. They can move huge amounts of water and cause devastating storm surges when they reach land. Yet they are also part of the planet's heat distribution system. Earth receives more solar energy near the equator than near the poles. Atmosphere and oceans transport heat away from the tropics. Tropical cyclones are one part of that enormous planetary circulation. Weather can therefore look chaotic locally while participating in large-scale physical processes across the entire planet. Chapter 3:3. The water cycle never really stops. Water is constantly moving. A molecule of water may spend time in an ocean. Then evaporate. Travel through the atmosphere. Condense into a cloud. Fall as rain. Enter a river. Freeze into a glacier. Melt. Flow underground. And eventually return to the ocean. The same water can move through these systems repeatedly. Earth's water cycle has been operating for billions of years. Individual molecules may have been part of ancient oceans. Some water you drink today may have once been inside a dinosaur. Some may have fallen as rain thousands of years ago. Some may have been frozen in an ancient glacier. Water is recycled continuously. But access to fresh water varies enormously around the planet. Some regions receive abundant rainfall. Others receive almost none. This uneven distribution is one of the most important factors shaping ecosystems and human civilization. Ancient civilizations often developed around rivers dot the Nile, the Tigris and Euphrates, the Indus, the Yellow River. Water supports agriculture. Agriculture supports cities. Cities support civilizations. In this sense, the history of humanity is deeply connected to Earth's water cycle. Chapter 34. Earth's oceans are still mysterious. We have mapped much of Earth's surface from satellites. But that doesn't mean we completely understand what lies beneath the ocean. The deep sea remains one of the least explored environments on Earth. Pressure increases dramatically with depth. Sunlight disappears. Temperatures can become extremely cold. Yet ecosystems thrive. Hydrothermal vents produce mineral-rich fluids that support unusual biological communities. Instead of relying directly on sunlight, some microorganisms use chemical energy. These microbes support food webs involving specialized animals. Scientists have discovered organisms that were previously unknown. They have found ecosystems adapted to pressures and temperatures far beyond ordinary human environments. The deep ocean also contains enormous geological structures. Mid-ocean ridges stretch for tens of thousands of kilometers around the planet. These ridges are associated with the creation of new oceanic crust. Deep trenches mark some of Earth's most extreme environments. The seafloor is therefore not flat. It contains mountains, valleys, volcanoes, plains, trenches, and enormous geological structures. If you could drain Earth's oceans and stand on the seafloor, you would discover a landscape almost as dramatic as the continents. The difference is that nearly all of it is hidden beneath kilometers of water. Chapter 35. Earth's oceans help control temperature. The oceans absorb enormous quantities of heat. This makes them crucial to Earth's climate. Water has a high heat capacity, meaning it can absorb large amounts of energy without changing temperature as rapidly as many other substances. Ocean currents transport heat around the planet. Warm water can move toward higher latitudes. Cold water can move toward the equator. This circulation influences regional climates. For example, ocean currents can make some coastal regions warmer or cooler than their latitude alone would suggest. The ocean also absorbs carbon dioxide from the atmosphere. Some of that carbon becomes part of marine ecosystems. Phytoplankton use carbon dioxide during photosynthesis. When organisms die, some of their carbon sinks into deeper water. The ocean therefore participates in the global carbon cycle. But the relationship is complicated. As oceans absorb more carbon dioxide, seawater chemistry changes. This can affect organisms that build shells or skeletons from calcium carbonate. Coral reefs are particularly sensitive to changes in temperature and chemistry. The ocean is therefore both a climate regulator and a biological system. Its influence reaches from the deepest trenches to the atmosphere above. Chapter 36. Earth has natural recycling systems. Earth is constantly recycling materials. Rocks weather. Sediment moves. Minerals dissolve. New rocks form. Tectonic plates carry material downward. Volcanoes return material to the surface. Water transports chemicals across continents. Plants absorb nutrients. Animals consume plants. Decomposers return nutrients to soil. Carbon moves through the atmosphere, oceans, rocks, and living organisms. Nitrogen cycles through the atmosphere, soil, oceans, and biological systems. Phosphorus moves through rocks, soil, water, and life. These cycles help keep Earth's systems functioning. The planet doesn't receive large supplies of new material from outside. Instead, much of what life uses is recycled. The atoms in your body have extremely ancient histories. The carbon in your cells may once have been part of an ancient organism. The oxygen you breathe has passed through countless biological and chemical processes. The calcium in your bones originated from geological materials. In a literal physical sense, living organisms are made from ancient planetary material. The boundary between geology and biology is therefore less clear than it first appears. Life is built from Earth's recycled atoms. Chapter 37 Earth's sky can produce spectacular optical effects. The atmosphere can create extraordinary visual phenomena. Rainbows appear when sunlight interacts with water droplets. Light enters a droplet, bends, reflects internally, and exits. Different wavelengths bend by slightly different amounts, separating the colors. Halos can appear around the sun or moon when light interacts with ice crystals in high clouds. Mirages occur because light bends as it travels through layers of air with different temperatures and densities. Crepuscular rays can appear when sunlight passes through gaps in clouds or other structures. Auroras occur when charged particles interact with the upper atmosphere. These phenomena can make the sky appear almost magical. But each has a physical explanation. The beauty of Earth doesn't become less impressive when we understand it. In many cases, it becomes more impressive. A rainbow is not simply a colorful arc. It is a geometric consequence of light, water, and the observer's position. An aurora isn't simply glowing paint across the sky. It is evidence of interactions between Earth and the sun. The atmosphere is a giant optical laboratory. And every day, somewhere on Earth, it creates another experiment. Chapter 38 Earth is constantly bombarded by space. Earth may feel isolated from space, but it isn't. Particles from the sun constantly stream past us. Cosmic rays arrive from distant astrophysical sources. Tiny pieces of rock enter Earth's atmosphere, but most are extremely small. As they heat and glow while passing through the atmosphere, we see meteors. Occasionally, larger objects survive the journey and reach the ground as meteorites. Earth is therefore continuously exchanging material with space. Most of this material is harmless. The atmosphere protects the surface from many small objects. But larger impacts have happened throughout Earth's history. Some created enormous craters. Others produced global environmental consequences. The Moon's heavily cratered surface provides a visible reminder that impacts are part of planetary history. Earth's surface hides many ancient impact structures because erosion, tectonics, vegetation, and oceans continually reshape the planet. The atmosphere and geology therefore erase some of the evidence, but the bombardment never completely stops. Earth is part of the solar system, and the solar system is part of a galaxy filled with moving objects. Our planet is constantly interacting with its cosmic environment. Chapter 39 Earth's days are getting longer. Earth's rotation is gradually slowing. The effect is tiny over a human lifetime, but it becomes significant over geological timescales. The main long-term mechanism is tidal interaction with the Moon. As Earth's oceans respond to lunar gravity, friction dissipates rotational energy. That energy contributes to changes in the Moon's orbit. The result is that Earth's day gradually becomes longer. Ancient organisms can provide evidence of this. Growth patterns preserved in fossilized organisms sometimes contain clues about ancient day lengths and seasonal cycles. Hundreds of millions of years ago, Earth experienced more days per year because each day was shorter. Over immense periods, Earth's rotation has slowed. But Earth's rotation isn't perfectly smooth. Atmospheric circulation, ocean movements, earthquakes, and processes inside Earth can produce tiny changes. Even the distribution of mass on the planet can influence rotation. This means Earth behaves like a complex rotating physical system. The length of the day isn't an absolutely fixed number. It changes. Very slowly. but it changes. Chapter 40. The North Pole is not fixed. When we think of the North Pole, we may imagine a permanent point at the top of Earth. But there are several different concepts of north. Geographic north refers to the rotational axis. Magnetic north refers to the direction toward Earth's magnetic north region. They are not the same, and magnetic north moves. Earth's magnetic field is generated by processes in the outer core. Because the fluid metal is constantly moving, the magnetic field changes. The magnetic poles can drift. Over geological timescales, the magnetic field can even reverse. Compasses respond to the magnetic field, not directly to Earth's rotational axis. This distinction has been important for navigation throughout human history. It has also become a powerful tool for scientists. When volcanic rocks cool, magnetic minerals can align with Earth's magnetic field. Those rocks can preserve evidence of the field's direction at the time they formed. By studying rocks on the ocean floor, scientists discovered symmetrical magnetic patterns that helped confirm seafloor spreading. This became important evidence for plate tectonics. An invisible magnetic field, therefore, helped reveal the movement of Earth's continents. Chapter 4:1 Earth's continents were once very different. Imagine a world where Africa and South America are separated differently. Imagine India as an island traveling across an ancient ocean. Imagine Antarctica, positioned much farther north. That was Earth's past. Continents move. Climate zones move with them. This means a location that is tropical today may once have been near a pole. A desert may once have been underwater. A mountain range may have been buried beneath sediments. Scientists reconstruct ancient geography using fossils, rock types, magnetic evidence, and geological structures. If the same fossil species appears on continents now separated by oceans, that can provide evidence that those landmasses were once connected. Ancient glacial deposits can reveal where continents were positioned relative to the poles. Coal deposits can reveal that forests once grew in regions that are now cold. Earth's map is therefore a historical document. Today's geography is only one configuration in a constantly changing planetary system, and the map will continue changing. Chapter 4:2 Earth's future continents may look completely different. The continents are still moving. If current tectonic trends continue for tens or hundreds of millions of years, Earth's geography will look dramatically different. The Atlantic may continue expanding. The Pacific is being consumed along several tectonic boundaries. Australia is moving northward. Africa is moving toward Europe. The Red Sea is gradually widening. East Africa is experiencing tectonic processes that may eventually produce a new ocean basin. These processes are incredibly slow. No human will notice a continent moving a few centimeters during a normal day. But geological time changes everything. A coastline can move. An ocean can close. A mountain range can rise. Another can disappear. In the distant future, Earth's continents may assemble into another supercontinent. Scientists have proposed several possible configurations, although the exact future arrangement is uncertain. Earth's surface is therefore never finished. The world map we teach children today is temporary. It is simply the latest frame in a movie that has been playing for billions of years. Chapter 4:3 Earth's sun will eventually change. Earth's future is connected to the sun. The sun is a star. Like all stars, it changes over time. Today, the sun is in a relatively stable phase called the main sequence. It generates energy through nuclear fusion in its core. But the sun will not remain exactly as it is forever. Over billions of years, the sun will gradually become more luminous. This will affect Earth's climate. Long before the sun becomes a red giant, Earth's surface conditions may become increasingly difficult for complex life. Eventually, the oceans could be lost. The atmosphere could change dramatically. The planet may become far less hospitable to life as we know it. Much later, the sun will expand into a red giant. The exact fate of Earth during this stage is complex and depends on how the sun's expansion and mass loss interact with Earth's orbit. But the important point is that Earth is not eternal. Neither is the sun. The planet has a beginning. It has a long middle chapter, and eventually its environment will change beyond recognition. This may sound depressing, but on astronomical timescales, change is normal. Stars evolve, planets evolve, galaxies evolve. Nothing remains exactly the same forever. Chapter 44. Earth is a rare kind of world. We have discovered thousands of planets beyond our solar system. Many more probably exist. Some are rocky. Some are giant planets. Some orbit their stars extremely closely. Others orbit much farther away. Some may have atmospheres. Some may contain oceans. But Earth remains special to us because it is the only planet we know with confirmed life. It has liquid water at the surface, a protective atmosphere, a magnetic field, active geology, a long-term carbon cycle, a stable star, and billions of years of biological evolution. None of these conditions alone guarantees life, but together they created an environment in which life flourished. And life didn't remain simple. It evolved from microscopic organisms into enormously complex ecosystems. Eventually, intelligent organisms appeared. One of those organisms developed technology capable of observing galaxies billions of light years away. That is perhaps the strangest fact about Earth. A small rocky planet orbiting an ordinary star produced creatures capable of studying the universe itself. When you look up at the night sky, you are not separate from the cosmos. You are part of it. The atoms in your body were created through ancient cosmic and planetary processes. You are made from the same universe you are observing. Chapter 4-5 Earth is home to a vast biosphere. Life exists almost everywhere on Earth where conditions allow it, from deep ocean trenches to high mountains, from deserts to tropical forests, not from polar ice to underground rocks. The biosphere extends across a huge range of environments, and microorganisms dominate many of these systems. Microbes live in soils, oceans, rocks, ice, sediments, inside plants, inside animals. Some live in environments without oxygen. Others survive extreme acidity or salinity. Humans tend to notice large animals. But microscopic life is fundamental to Earth's functioning. Microorganisms recycle nutrients, break down organic material, transform chemicals, support food webs, influence atmospheric composition, and interact with nearly every ecosystem. The visible world is therefore only the surface of Earth's biological complexity. If you could shrink yourself down and explore a handful of soil, a drop of seawater, or the surface of a leaf, you would encounter an enormous microscopic universe. Earth is not merely inhabited. It is saturated with life. Chapter 46. The strangest fact may be that Earth exists at all. Consider the chain of events required for your existence. A star had to form. Planets had to develop around it. Earth had to assemble. The planet had to retain an atmosphere and water. Chemistry had to become biology. Life had to survive enormous environmental changes. Cells had to evolve complexity. Multicellular organisms had to emerge. Mass extinctions had to occur. New ecosystems had to replace old ones. Mammals had to evolve. Primates had to evolve. Humans had to appear. And eventually, you had to be born. Change any number of events in that chain, and the outcome could have been different. Earth's history is therefore a story of extraordinary continuity mixed with enormous disruption. The planet survived. Life survived. And life transformed. The world around us is not the product of one single event. It is the result of billions of years of interactions. Geology, chemistry, physics, biology. Climate. Astronomy. All working together. Earth is the result. Chapter 4:7. We are still discovering new things about Earth. It is easy to think that scientists have already discovered everything important about our planet, but that isn't true. New species are discovered regularly. New geological structures are mapped. New microorganisms are identified. Scientists continue to study Earth's deep interior. The deep ocean remains incompletely explored. Antarctica continues to reveal hidden landscapes beneath its ice. New evidence can change our understanding of ancient climates. Modern satellites allow scientists to observe Earth's atmosphere, oceans, forests, glaciers, and ice sheets in extraordinary detail. Earth science is not finished. The planet is too complex. There are too many interacting systems. And many processes occur on timescales far longer than human history. Some changes happen in seconds. Others take thousands of years. Others require millions or billions of years. Understanding Earth, therefore, requires combining observations across enormous scales of time and space. From microscopic organisms to global climate systems. From a single earthquake to the movement of continents. From one cloud to the entire atmosphere. The more we learn, the more interconnected the planet appears. Chapter 4:8. Earth is a planet of constant change. Nothing on Earth is truly permanent. Mountains rise and erode. Rivers change course. Coastlines move. Glaciers advance and retreat. Forests grow and disappear. Species evolve. Species go extinct. Oceans open and close. Continents collide. Volcanoes build new land. Earthquakes reshape landscapes. The atmosphere changes. The climate changes. Even the length of a day changes. This constant transformation is one of Earth's defining characteristics. The planet may appear stable because human lives are short compared with geological time. But if you could watch Earth over millions of years in accelerated time, it would look alive with movement. Continents would drift. Mountains would rise. Oceans would appear and disappear. Ice sheets would expand and retreat. Species would emerge and vanish. Earth would look less like a static object and more like a constantly evolving system. And that is perhaps the best way to understand our planet. Earth is not something that simply is. Earth is something that is always becoming. Final chapter. The planet beneath our feet. Now return to where we began. You are sitting somewhere on Earth. Perhaps you're indoors. Maybe it's nighttime. Outside, the atmosphere extends upward into space. Clouds are moving. Winds are circulating. Somewhere on the planet, rain is falling. Somewhere else, snow is accumulating. A volcano may be releasing heat from Earth's interior. An earthquake may be occurring deep beneath the surface. A whale may be moving through the darkness of the ocean. A tiny microorganism may be reproducing in soil. A glacier may be slowly flowing. A river may be carrying sediment toward the sea. And beneath all of it, Earth's tectonic plates are moving. Only centimeters per year. But they are moving. Above everything, Earth is orbiting the Sun at more than 100,000 kilometers per hour. The Sun is moving through the Milky Way. And the Milky Way is moving through the universe. You are never actually standing still. You are part of an enormous cosmic journey. And the planet beneath you is far stranger than it appears. It is a world with a molten interior, a magnetic shield, a thin atmosphere. Deep oceans, moving continents. Ancient forests, frozen deserts, volcanic islands, underground ecosystems, gigantic storms. Invisible cycles, and billions of years of history. But perhaps the most remarkable fact of all is this: Earth is the only world we currently know that is home to life. Every human being who has ever lived was born here. Every civilization began here. Every human story unfolded beneath this atmosphere. Every photograph of Earth from space shows the same tiny world. One planet, one biosphere, one home. From the first single-celled organisms to modern civilization, everything we know about life has happened on this small planet. And when you look at Earth that way, familiar things become extraordinary. A cloud is no longer just a cloud. It is part of a planetary water cycle. A mountain is not simply a mountain. It is a temporary geological structure. The ocean isn't just a huge body of water. It is one of the engines that regulate Earth's climate. A forest isn't simply a collection of trees. It is a complex biological network. And the ground beneath your feet isn't motionless. It is part of a planet that is constantly changing. So the next time you look at the sky, walk beside an ocean, stand beneath a mountain, watch a storm, or simply feel the ground beneath you, remember that you're experiencing only one tiny moment in a planetary story that has lasted for roughly 4.5 billion years. A story that began before humans existed. A story that will continue after us. A story written in rock, water, ice, atmosphere, and life. The story of Earth. Our planet. Our home. And perhaps one of the most extraordinary worlds in the universe. Thank you for watching, and wherever you are on Earth tonight, take a moment to look around, because this familiar planet is far more amazing than we usually realize.